Hello, and welcome back to Returd. I'm Amy. Today we're going to talk about something crucial in the world of AI, the report card. How do we know if an AI model is actually any good? It seems simple, but the answer is surprisingly deep. Imagine you've built an AI to sort fruit. You test it on a basket of 100 fruits. 80 are apples and 20 are oranges. The model correctly identifies 85 of them. That's 85% accuracy, right? Sounds pretty good. But what if I told you the model correctly identified all 80 apples, but only 5 of the 20 oranges? It's a master at finding apples, but it's terrible at its other job, finding oranges. If your goal was to build a perfect orange sorter, this A-grade model is actually a complete failure. This is the central challenge we face. Accuracy, while easy to understand, can be a trickster. It often hides the real story. To truly understand our AI, especially for critical tasks like spotting rare diseases or stopping fraud, we need a much better report card. Today, we'll build that report card piece by piece. Before we can get to any grades, we need to understand the raw data. In AI, this is called the confusion matrix. It's not a metric itself, but a simple table that shows us exactly where the model got things right and where it got, well, confused. Let's use a more serious example, a medical AI that tries to detect a disease. The positive class means the person has the disease. The negative class means they don't. Our model's predictions create 4 possible outcomes. First, the good stuff. If the person has the disease and the model says so, that's a true positive, or TP. If the person is healthy and the model agrees, that's a true negative, or TN. These are our successes. Now for the errors. If the model says a healthy person has the disease, that's a false positive. This is also called a type 1 error. Think of it as a false alarm. But the most dangerous mistake is this one. The person has the disease, but the model says they're healthy. This is a false negative, or type 2 error. The model missed it completely. This simple grid is the source of truth for everything else we're about to discuss. Every single metric we calculate comes from these 4 numbers: TP, TN, FP, and FN. Let's start with the one we already know, accuracy. It asks the simple question, what fraction of all predictions did the model get right? You just add up the correct predictions, TP and TN, and divide by the total number of predictions. But remember our fruit sorter? Or imagine a fraud detection system where 99.9% of transactions are normal. A lazy model that just predicts not fraud every time will be 99.9% accurate, but it will miss every single fraudulent transaction. It's useless. This is why accuracy is dangerous for imbalanced datasets. This brings us to our next metric, precision. Think of it as the purity metric. It answers the question, of all the times the model predicted positive, how many were actually correct? You need high precision when the cost of a false positive is high. Take spam detection. You would rather let a single spam email slip into your inbox, a false negative, than have an important email from your boss mistakenly sent to the spam folder, a false positive. Next up is recall. If precision is about purity, recall is about completeness. It answers the question, of all the actual positive cases in the world, how many did our model find? You need high recall when the cost of a false negative is high. This is the opposite of the precision scenario. For medical diagnosis, you absolutely cannot miss a patient who has a disease. A false negative could be fatal. You'd rather have a false positive, telling a healthy person they might be sick and need more tests, than miss a real case. Now you might be thinking, can't we have both? Usually no. There is an inherent trade-off. If you lower your standards to catch every possible sick patient, high recall, you'll inevitably flag more healthy people by mistake, low precision. It's a balancing act. So what if you need a balance of both? Enter the F1 score. It's the diplomat of metrics. The F1 score is the harmonic mean of precision and recall, which is a fancy way of saying it provides a single score that balances both concerns. The F1 score is your best friend when you have imbalanced classes, and the cost of both false positives and false negatives is significant. It's often a much better starting point than accuracy. All right, that was a lot of theory. Let's make this real with some code. Let's say we have our true labels and our model's predictions. We can use Python's scikit-learn library to calculate everything we just discussed instantly. See? With just a few lines of code, you can generate the entire report card for your model. The confusion matrix here shows us we have 4 true positives, 4 true negatives, 1 false positive, and 1 false negative. But we can go even deeper. Many models don't just say yes or no. They output a probability score, like I'm 75% sure this is a positive case. We then pick a threshold, say 50%, to make the final decision. Curve-based metrics evaluate the model across all possible thresholds. The first is the AUC curve, which stands for Receiver Operating Characteristic. It plots the true positive rate, which is just another name for recall, against the false positive rate. A perfect model would have a curve that goes straight up and across, hugging the top left corner. The area under this curve, or AUC, gives us a single number from 0 to 1. An AUC of 0.5 is no better than random guessing. An AUC of 1.0 means the model is a perfect classifier. It's a great way to measure the model's overall ability to distinguish between classes. However, for our imbalanced data problems, the ROC curve can be too optimistic. Instead, we can use a precision recall curve. It does exactly what it says. It plots precision versus recall at different thresholds. This gives a much more honest picture of performance on the rare positive class. So let's put it all together. Which metric should you use? It always depends on your goal. Now it's your turn to think. I'm going to ask you a few questions. Pause the video and think about your answer. First, you're building an AI to predict if a user will click an ad. Clicks are very rare. Which single metric is a good starting point? The answer is the F1 score. Clicks are rare, so it's an imbalanced dataset. You want to find users who will click recall, but you also don't want to annoy users with irrelevant ads. Precision. The F1 score balances these two needs perfectly. Second question, an autonomous car's AI needs to identify pedestrians. What is the most critical metric here? Precision or recall? And why? It's absolutely recall. A false negative missing a pedestrian is catastrophic. A false positive breaking for a shadow it thinks is a person is an inconvenience, but it's safe. The cost of missing a positive case is infinitely high, so you must maximize recall. Last one. Model A has 95% accuracy and an AUC of 0.75. Model B has 92% accuracy and an AUC of 0.85. Which model is likely better and why? Model B is likely the better overall classifier. The AUC score of 0.85 shows it has better power to distinguish between classes across all thresholds. Model A's higher accuracy might just be a symptom of the accuracy paradox on an imbalanced dataset. So remember, accuracy is just the cover of the book. To truly understand your AI, you need to read the whole report card, the confusion matrix, the trade-offs between precision and recall, and the stories told by the curves. This is how you go from just building a model to building a model you can trust. Thank you for joining me on Returd today. If this helped you see AI evaluation more clearly, give this video a like, subscribe for more lessons, and let me know in the comments what topic you'd like us to demystify next. Until then, keep learning.